Hi, so this video, hopefully shorter than the other, will be showing you spectra and models of the molecules. So this spectrum here is for methane, and all four hydrogens are equivalent, and the peak's showing up way down here right next to TMS. And the reason is because the carbon only has hydrogens on it. And having another carbon on there actually does tweak things to go downfield a little bit. So if I click on the peak, you'll see it's those four, which we knew. Okay. So here's ethane, and we have 6 hydrogens now, and they are all equivalent to one another, and so we get another singlet peak here, and you notice it's been pulled downfield a little bit, and that is because this carbon here has more pull than hydrogens, which means that this is affecting these hydrogens and what their environment is, and then this one is affecting these hydrogens and what their environment is. So it gets moved downfield, and of course it's just that one peak. Okay, so now here I have propane, and this is a secondary reference peak. And here in propane we have one peak here, which is those 6 hydrogens that are all equivalent to one another, and then this different peak here, which is those 2 that are there. Now if I turn on the integration, we can see that here we have the height can be measured here, and then the height can be measured here, and it's in a 1:3 ratio, or pretty close to it. And 1:3 can be also 2:6. The peaks here have structure. So this peak here, very much like in the isopropyl alcohol one from the other video, is being split. This one is the 6 hydrogens from the 2 methyl groups. Only this time it's being split into a triplet here. It's short, tall, short. Okay, and it's being split into a triplet because there are 2 vicinal hydrogens. In that other example, there was only 1 vicinal hydrogen, and there was the OH group. So there's going to be a triplet here instead of that doublet we saw in the other example. But over here, this peak being for the 2 methylene CH2 hydrogens, that looks just like the other peak we saw on the other spectrum. It is a septet. It's being split by these other 6 hydrogens here. So same kind of shape, but it's in a very different location than the other one was in the last spectrum. The other one was out here because there was an O, and this one there's no O, so it's pulled on back into this position. So here I've got butane, and there's 2 blobs here. There's 2 kinds of hydrogens. It's like, well, hey, they got 10 hydrogens. How can there only be 2 kinds? Well, there are 2 kinds. There's these 4, which are all exactly the same, and then there's these 6, which are all exactly the same, and are different from the other 4. And if we look at the integration, we will see it's a 2:3 or 4:6 ratio. And if we look at the splittings, again, we're not zoomed in, but here we've got a short peak, a big peak, a short peak. That's a triplet. And the reason that this is a triplet is because each one of these has 2 vicinal hydrogens. 2 vicinal hydrogens splits into a triplet. And then for this one, it's a quartet where you can see the 2 little tiny peaks. They're not very, very far apart on this image. We'll see other images that are more expanded. And it's short, tall, tall, short. 1:3 to 3:1 approximately. And these hydrogens here are each going to be split by the 3 hydrogens that are vicinal. The other ones are not considered vicinal because they are identical. Identical is not the same as vicinal. So they're split by 3, so we have a quartet there. Okay. So now, I had gone methane, ethane, propane, butane. And so now I've thrown in a new wrinkle, which is the double bonds. The CC double bond, all 4 hydrogens are exactly the same. They're not splitting each other. It's a singlet again. but it's way, way, way over here at 5. And the reason for that is that the electrons in the pi bond, okay, those electrons in the pi bond are actually doing quite a substantial amount of shielding. Not shielding, of de-shielding. Sorry for the pause there. Of de-shielding, the electrons are being pulled out of the plane with the hydrogens and being put into the above and below the plane pi bond. And so that actually means that it is being de-shielded. The electrons are being slurped away as we come out to that position. And that is true for the hydrogens on a double bond. On a triple bond, because of the geometry of the, let's see if I can spin this around. Because of the geometry of having the 2 pi bonds, it's actually not as de-shielded. It's actually back here again. Again, it's all about the geometry of all of these various spins, but they are, of course, equivalent, so you only get 1 peak. Now here I've got one that's a little bit interesting. So this one is diethyl ether or ethoxyethane, either one. There are 10 hydrogens, so very much like the butane we saw a couple of minutes ago, there are 2 peaks. The peaks are even very much like they were in the butane. Here we've got this peak, which is a triplet, which is the methyl hydrogens being split by the 2 vicinals. And out here we've got a quartet. And really the only thing different of this spectrum from the other spectrum is that this quartet got shifted over. So let me go to right there, I believe. So this one, you had the triplet and the quartet, and for this one, you've got the triplet and the quartet, but this is shifted a lot, and that's because this oxygen is right nearby. So the oxygen on that carbon is going to de-shield the peak due to these hydrogens substantially. It's very similar to that 3.8 on the one from the other video. Okay. And the integration again is 2 to 3. Okay, and so when you see a 2 to 3 ratio and it's a quartet and a triplet, that's a really big sign for an ethyl grouping. That would be the area 3 here split by these, so it's a triplet. The area 2 here split by 3, so it's a quartet. So that's really, really indicative of an ethyl group. Now here I've got THF, tetrahydrofuran, which is actually also an ether. It's a cyclic ether, and so 2 hydrogens are missing. Degree of unsaturation is 1. There's only 8 hydrogens, not 10. This is a good solvent. It's a slightly polar, but not hydrogen bonding solvent. And in this one, integration, we've got 2 peaks that are equivalent in area. And we've got the ones that are closer to the oxygen. These are equivalent to each other, these 4 hydrogens. And we've got the ones that are further from the oxygen. So which peak do you think is going to be the ones that are closer to the oxygen? Well, hopefully you thought that one through. But this is closer to the oxygen, is more de-shielded, it's more downfield. And notice that it is a triplet. You got the little stubby 1 to 2 to 1s. And it's a triplet because each of these hydrogens is being split by 2 vicinal hydrogens on the next door carbon. And then this one, of course, is the ones that are further from the oxygen. Also is a triplet. Well, 1 to 2 to 1-ish, 2 little peaks, 1 big peak. Again, each one split by 2 vicinal hydrogens. Now, I've got one more here to show you, which is benzene. And we've got an interesting feature here. So first of all 6 of them are equivalent. And very much like with the ethene, the doubly bonded one, that peak has been pulled way, way, way on down here to 7.5. So it's unsplit. But again, the ring, okay, and the electrons in the super pi bond business going here, those electrons are being pulled away from the area of the hydrogens out of their plane. And so we're going to have a de-shielding effect. As a matter of fact, this is the region of the spectrum that's indicative of benzene. If you have a molecule that has a lot of degrees of unsaturation, you know there are double bonds and rings. This has 4 degrees of unsaturation, the ring and the 3 pi's. And then you look at the NMR and you see, oh, look at that out here in the 7 to 8 range, that sort of range. You're going to say, oh, there's a benzene ring in this molecule.